rainbow color palette goes from white 0 to red 100%, and it's designed for a traditional ASME type inspection where an 80% calibration allows visualization of the color palette at 3 and 6 dB drops. When the beam is properly calibrated across all of the angles in this axis for one flaw or side drilled hole, and it's also calibrated in TCG for time of flight. This allows the entire beam to have a consistent color palette across multiple TCG points. Our amplitude readings come directly from the readings at the top of the data views, and they're relative to either gate A or B. Amplitude program in the MX2 also allows either a peak amplitude, like we see here in E, or a first peak amplitude, as seen here in D. And the natural, traditional weld inspection, of course, will be using peak amplitude. And this is going to determine the color pixel we see for one particular point is derived from the amplitude in gate A based on the logic we've programmed. So a phased array is most associated with the sector scan display. The sector scan display is a way of visualizing multiple A scans coming from one probe and what we call one group at different angles through the projection of the weld. The MX2, you see, can have a full screen displayed A scan where selecting the minus button will return all of our menu items. Things that help us on the sector scan display, of course, are the weld overlay, which is only possible in a true depth ruler, skip overlays that represent the ID and OD of the component. We can visualize our gate area. The C-scan data and the readings we're going to generate from this S-scan are dependent on the A-scan we select within our gated area. And the data cursor, as I move the data cursor, we will see the associated A-scan for that angle. All of the information in the A-scan is available in this S-scan. And the S-scan is available in either a true depth display, like you see here, where it's easily projected over the component overlay or weld overlay, and it's easy for the operator in his head to visualize the inspection in the part. The downside of this type of display is that it doesn't efficiently use the entire space for the data view. An uncorrected S-scan, where the range is the same on every A-scan and it's not corrected for depth, has an advantage for several of the applications, like crack detection using the ID creeping wave or WSY type technique that we will see. And again, notice the sound path ruler on this S-scan and the true depth ruler of a different color on another. In addition to the A-scan, there's also the B-scan view. The B-scan view is a 2D view that represents the scan axis or probe movement versus the ultrasound axis. It's not dependent on a gate like the C-scan. So in this view, we can see the geometry from the cap here at the T1 line, the slight geometry from the bottom at B0, and as I change through the angles, this is a visualization of only one focal law or angle at a time. It's very helpful in length sizing and tip characterization for cracks and other types of defects. The C-scan comes in several different varieties depending on if you're using a sector scan or a linear scan, but it's a projection of the top view. So on one of the axes, we will see the scan movement or the scan axis, and on the other axis, we will see the gate data for every focal law, typically 45 through 70 degrees on a weld inspection. What that translates to in the MX2 is an uncorrected amplitude C-scan. This one pixel at this position on the scan axis, detected by this angle in the focal law, represents the maximum amplitude of any signal that appears in the gate. It's a type of also amplitude strip chart, but allows us a top view, being able to visualize all the gate data from all of the focal laws in one display. This display is typically used for our length sizing. We're going to associate the length of the flaw with the scan axis and the depth and the height of the flaw on the ultrasound axis. So as the scanner is moved on the component, we are populating the display on the scan axis. Every 1 millimeter of scanner travel here represents 1 millimeter on the C-scan display. So we're going to use 3 cursors. The data cursor is where we're going to read our statistics at the top of the MX2 and where we will associate the A-scan for that particular indication. The scan axis reference cursor here represents the start of the flaw, and the scan axis measure cursor here represents the end of the flaw. Every axis, scan, index, ultrasound, has 2 cursors associated with it that are used for measuring things, either something between them, the delta between the 2, or the position of the cursor. So in the readings that we will use for our length sizing, we will identify the start of the flaw with the scan axis reference cursor. At this example, 280 millimeters. The end of the flaw with the reference cursor on the scan axis, or SM. And this is at 288 millimeters. The delta between the 2 is the length of the flaw, 7.5 millimeters. So there are several methods for where do I place those cursors exactly. Depending on your procedure and code, common methods are 6 dB drop techniques, 3 dB drop techniques, rapid drop, and what we would tell people, I get asked this question often in my training classes, what is the technique I use for length and depth sizing? And we can give some fairly generalizations, but with your procedure, based on your particular weld, bevel, and weld process, with the benefit of some qualification samples and some destructive testing of your sizing technique, those basic amplitude drop or rapid sizing techniques can be refined to dramatically improve the accuracy. What works in one environment at 6 dB might not work at another environment. If I were measuring the width or depth of side drilled holes in the cow block, I would probably use more of a 1 dB drop technique. And we'll see some examples of each of those when we start looking at some data flaws in the actual sample. In this example, a dB drop technique wouldn't work because we can see on the scan axis the flaw is intermittent. So like most of our techniques in phased array, it becomes very much a visualization of the flaw on the C-scan and the S-scan and B-scan. In this example, we have an intermittent sidewall lack of fusion that changes both height and depth position intermediately where the maximum is seen here. Identifying that with the cursors allows me to measure it accurately as the delta between the reference and measure cursor on the scan axis. When we're talking about a manual inspection with no scanners, we're generally limited to what we mark on the pipe. But once we hook a scanner or encoder to the probe, now we can get a precision length measurement. The actual definition of our link sizing accuracy would be directly related to the steps per millimeter or the resolution of the encoder. In this case, this is a type of square wave quadrature encoder, and every millimeter of travel, this generates 12 triggers to the instrument. So the definable minimum smallest flaw you could detect or size would be limited to the resolution of the encoder. But typically in our applications, we will use either 1/2, 1 millimeter, or 2 millimeters based on our procedure. In the 2010 ASME Section 5 phased array E-scan and S-scan examination requirements, flaws or component thicknesses smaller or thinner than 75 millimeters or 3 inches, we would use a 1 millimeter resolution. And for larger than that, we would use a 2 millimeter. If we're using a 1 millimeter inspection resolution, we could expect a worst case scenario of plus or minus 2 millimeters in our sizing technique. As we get smaller diameter piping with thinner components, the mathematics behind the reject accept is very dependent on a very tight, small inspection resolution. Other things that improve our link sizing capability is probe technology. Both the frequency of the probe, a 2 megahertz probe typical of AWS inspection, does not have the ability to link size as accurately as a higher frequency, but it would perform better for detection. In some of the applications using advanced probes optimized for link sizing, these would have internal curved radius that allow us on the C-scan and the B-scan to more finely define the length of the flaw. As we can see here, without the use of curved arrays, my ability to place the cursor at the direct end of the flaw is compromised somewhat. When we internally curve the radius, it gives us improved link sizing. The downside of the internal curved radius is that it is limited to a range of thickness instead of an indefinite range of thickness. And two applications very common for this are the small diameter boiler tube inspections typical of the Cobra inspection system that comes standard with those probes, and most of the pipeline construction high-speed girth weld systems like the Pipe Wizard benefit enormously from the improved link sizing probe technology. We often add a top channel in addition to the phased array to also improve our link sizing. Of our 256 available focal laws in the MX2, the A-scan from the top channel only uses one. It's fast, easy, and cheap to set up and configure on the instrument, and the longer we travel on our sound path and the fewer angles we have for resolution, the more important it is to improve for applications where we need 1 millimeter length, depth, and height sizing over long sound paths, such as in thick vessels. We're aided greatly by the use of Toft for our link sizing. Moving into depth and height sizing, this is directly related to the angle resolution. Our ability to define the top and the bottom of the flaw is directly related to the number of A-scans or the angular resolution that we program in the group. We see two examples here. At a 1 degree resolution, we would still, on any weld to up to about 25 or 30 millimeters, we would still expect a high precision inspection. When we're inspecting from only one position, such as in a one-line scan, we benefit more than in a manual inspection from a high resolution. In this case, 0.5 degree, but in some cases even 0.1 or 0.25 degrees. In this example, the high resolution of the A scans is directly related to speed and file size. The data file generated from this would be exactly double the size of this, but we would have dramatically improved length, depth, and height sizing. So similarly to length sizing, we're going to use the same type of cursors, but instead of on the scan axis or blue ruler, we're going to define these on the ultrasound axis or UT or depth ruler. So we have a reading in the OmniScan that is the reference cursor position on the ultrasound axis that you see here. We have another cursor that does the exact same thing, green, called the measure cursor. And then another reading called the U-M-R, which is the delta between the two. Any crack or indication that was determined to be connected to the ID or OD, one of those two cursors would be placed exactly at B0 or T1, representing the top or bottom of the component. And the other cursor would be used to define the center of the energy or the tip of the crack or the flaw. Using amplitude or time of flight tip diffracted type techniques, we will place these cursors in the appropriate position. In this example, we have a ID connected crack that has a through wall dimension of 3.61. This cursor defines the top of the crack. This cursor defines the bottom of the component, and we can see it's identifiable above and below B0, indicating a through wall ID connected crack. The flaw depth height sizing readings also for embedded flaws require us to define the top and the bottom. So in this example of sidewall lack of fusion, we're going to use, instead of a tip diffracted technique typical of cracks, we'll use an amplitude-based technique for favorable geometry and planar flaws where the orientation of the beam is close to perpendicular to the flaw. Notice also the characterization of this A-scan, very typical of sidewall lack of fusion, where we have a short rise and fall time, a high amplitude signal without much echo dynamic. So if the flaw appears at about 80% like this one does, and we can tell from the color palette here relative to this, typically new inspectors, junior inspection companies, or per jobs where there hasn't been any or little upfront engineering for refining the sizing technique, people would generally oversize the flaws. So we want to be conservative. We can see here the 3 dB drop and the 6 dB drop position. Somewhere in between those, based on your weld bevel and your weld process, we will determine. And this is best done if it's procedural. It's in your technique sheet, it's in your procedure. Very rarely do the codes actually tell us how they want flaws sized. It's dependent on the individual job or the company procedure to do that. So we've identified the sidewall lack of fusion here as a 3.64 through wall height dimension from a depth of 13 millimeters directly in the middle of it. That's based on the DA gate reading. And we identified the two cursors in the middle of the second half skip for our through wall dimension. And in this example, we're using about a 3 dB technique, a minus 3 dB technique that we can visualize right on the flaw using the color palette. Our sizing and depth and height sizing in particular is dramatically improved by advanced inspection techniques and more powerful instrumentation. The two images you see side by side here are a 10 millimeter high, 1 millimeter EDM notch. when we use a 5 megahertz probe and 32 elements in our aperture, we focus directly at the top of the tip, and we put many, many A scans inside the sector scan by using a 0.2 degree S scan. We can see how much clearer and sharper the indication appears. The two indications you see here are the leading edge tip and trailing edge tip diffracted signals from the notch. My ability to place a cursor accurately at the center of the energy is greatly improved compared to the same 5 megahertz probe with less elements using a 1 degree sector scan. And again, this also demonstrates the benefit of a 32 pulsar instrument as well. In the depth and height sizing, we do on the ultrasound axis. For the length sizing on the scan axis. In some of our applications, we must also define the width or the top view or index axis position. Again, placing my cursors on this axis, I get an IR representing the index reference, an IM representing the index measure, and the delta between the two. Looking at that same 1 millimeter tip notch, I see the position start, position stop, and if we're measuring the very center of the energy accurately, we can see our 1 millimeter delta between the two at a very precise depth, greatly aided by higher frequency probes, more elements in the aperture, and more angle resolution in the sector scan. We will take our readings for accuracy directly from the gate readings. It's poor practice and inaccurate to depend too much on the scales. There's a lot of tools built in to make our statistical readings useful. In this example of shear wave tip diffraction, we have a ID crack connected to the bottom of the component, and here we see the corner trap. We will search through the data looking for individual tips. Every one of these uniquely definable indications represents a different tip or facet of the crack. The deepest one you can find will represent the through-wall dimension of the crack. Again, seen here at 7.96 millimeters from the top, that's the depth, and the through-wall dimension would be the delta between the two cursors, so it would be a 4.54 millimeter through-wall dimension. When we have to define a segment that doesn't line up vertical or horizontal, such as the 3D segment tool in TomoView, we have the ability to do this as well. Similarly to all of the previous readings, this reading will define an XY position or a XY position from the reference cursor on both axes, an XY position from the measure cursor on both axes, and calculate the trigonometry between the two. So in this case, we have a through-wall height dimension, which is typical of our ASME codes, but a ligament or segment length of 9.25 millimeters using the UI-M-R reading. Typically, for most of our weld applications and code-based construction inspections, that reading isn't required. And again, TOFT benefits depth and height sizing, particularly on long sound paths. In this sector scan example you see here, it's about a 100 millimeter thick vessel. We're skipping off the bottom and on the second leg coming back through the volume. The farther each angle changes, the larger the gap between two A scans or focal laws. So we could have 3, 4, 5 millimeter gap between two focal laws, even at a 0.5 or 1 millimeter or 1 angle, 0.5 or 1 degree resolution. So for amplitude acceptance, this is very good because we can calibrate this and we know that color equals the same sensitivity from our calibration block. But my ability to size is dramatically diminished as time and the sound path travels. So again, a fast, cheap, easy way to add enhanced value when we need defect sizing in the range of 1 millimeter or less is to add the top probes and the top channel. The volumetric position is a critical indicator for where to excavate the component to make the repair. The VIA reading in the MX2 represents the volumetric position, where, from the top volume, of the indication on the index axis of the signal in gate A. Okay, so what that means is, on this side of the weld, left of center line, it's a negative number and typically associated with the skew 90 probe. And on this side of the weld, it would be a positive number. It's directly related to the probe distance, but once the probe distance is removed, or once the probe is removed from the component, the repairman needs to know I need to go -3 millimeters this way, down 7.96 millimeters this way, where I would be able to detect the flaw. Volumetric position. Where we're going to go now is to OmniScan PC, or Omni PC. It's a new product introduced by Olympus that allows the exact same user interface from the instrument to be viewed offline on a computer. To account for the touchscreen functions, there are numerous shortcut keys and mouse functions that make analysis fast and simple. So a short training between just to take over the touchscreen functions allows us to move and analyze and perform reports in Omni PC quickly and efficiently. So we're going to take a look on my Omni PC program. And as you see, we see almost the same user interface as the instrument, but spread out a little bit longer. Looking at this weld, this was from a Cobra one-sided inspection on a component that was 16 millimeters thick. So I see my skip lines here at B0 representing 16 millimeters in true depth and 32 millimeters representing the full skip. As I take this blue cursor here on the S scan to B0, this is represented here, and from B0 to T1, representing the full second leg or half skip to the top, is between B0 and T1. So it would continue B2, T2, T3, B4, so on and so forth. So looking at our C-scan that we see here, we performed an inspection from 0 to 300 millimeters at a 0.5 degree resolution. So where the scan started at 0, where the scan stopped at 300, every 1/2 millimeter, we have a slice of the weld represented by this data cursor. This data cursor shows me the slice of the sector scan. The color pixel that you see here at the cross section represents the maximum indication in the gate for the 50-degree angle at a position on the scan axis of 147 millimeters. So it's an intermittent defect, obviously, and if I zoom in on my S scan for the area of interest, and I step through each acquisition point, I'll be able to see the flaw. So I'll perform my length sizing first. I'm going to place a cursor at the rapid drop position of the end of the flaw, and I can take a peek at that position here using my data cursor. So here's the flaw start position. I'll place another cursor at the end of the flaw on the scan axis and visualize it in the S-scan. And I would record the flaw at the position of maximum amplitude. So my length sizing is represented, start at 120 millimeters, stopped at 155 millimeters for a dimension, a length dimension of 35 millimeters. Without moving my cursors on the scan axis, now I'll perform my depth and height sizing on the S-scan. Length on the C-scan, depth and height on the S-scan. So I'm going to place a cursor, and I can either use the mouse to double-click the cursor positions, or I could drag and drop them, or use the menu under Measurement, Cursor, S-scan, and manipulate them here. Our depth and height sizing only requires the UT axis, so I will just put the index cursors out of my view. I'm going to define the top and bottom of the sidewall lack of fusion based on about a 3 dB drop. I'll zoom in a little bit tighter. Now, as I walk the data cursor, I want to make sure no part of that is significantly higher or lower than what I've defined. In this example, I defined the top and bottom on this section accurately, but it looks like the flaw is much lower here. So I will move my cursors again and continue through the data. And when I'm satisfied I've defined the area well, I will move it back to the position of maximum amplitude. I'll put my cursor back on the hot A-scan. So the depth of the non-fusion, and we're looking in the second skip from the top down. I'll zoom out so we can take a little better look at this. So this is the first half skip of the weld, and this is the second half skip. I've defined the top and the bottom of that, so my through wall dimension is about 4.18 millimeters. That's the delta between these two cursors. My length was 35, amplitude was 75, and I'll just check that again and make sure there's not a hotter spot in there. 78. Okay, so we have rejectable non-fusion, sidewall lack of fusion. The volumetric position is 8 millimeters on this side of the weld. It is 24 millimeters in front of the probe position during the inspection. The maximum amplitude occurred at a depth of 4.2 millimeters from the top surface, and my sizing information is here. Taking a look at one more defect on this same data file, based on its location in the weld and the A-scan and S-scan characterization, we know this is lack of root fusion connected to the ID. Lack of root fusion, and it's connected to the ID. To size that, we would assume one of our cursors is directly at B0, and that's at a depth of 16 millimeters. So I'll just type it in directly. I will use my better indication on the second leg to identify the top at about a 3 dB drop. Okay, again, we typically always oversize defects, so we want to be conservative. Based on your weld bevel, based on your destructive testing and your procedure, somewhere in about a 3 to 6 dB drop, or in a rapid drop visualization of the flaw, you can arrive at a very tight specification of we would expect a 0.5 millimeter to 1 millimeter sizing accuracy in these type of techniques. Moving on to the next data file. We have a recorded one-line scan on a typical V-weld of a thickness of 12 millimeters. So we look through the weld and we see the flaw in the middle of the weld. When we teach weld inspection and weld flaw characterization, we generally promote 3 criteria. Location of the flaw. Was it detectable from both sides of the weld when that's possible, as a criteria 2? And the third criteria is the A-scan characterization, also the S-scan characterization, what it looks like. So here we see a volumetric flaw, multiple peaks, multiple facets, a very long rise and fall echo dynamic, and obviously it looks like porosity, and that's what it is. Sometimes this is difficult to distinguish from slag. If it's short isolated spots, they look very similar, but the short length, the multiple peaks and valleys, very typical of a porosity indication. The most difficult for ultrasound, phased array, or conventional UT to size and characterize, and the simplest for RT. Out here we see some lower level porosity as well that typically wouldn't be reject and probably wouldn't meet recording thresholds, but it's very close. But this one we will size. So I will place a reference cursor at the beginning of it and just take a look at it. There's going to be beam spread on different frequencies of probes, and beam spread differently depending on if you're using an internal radius curved probe or not. So your technique has to be somewhat specific to your own inspection strategy. Okay, we go through the porosity. This is where its maximum is, and we'll come all the way to the end. This is still little porosity indications, even though they're low level, and we lose it out here. Okay, so we'll place a measure cursor on that axis, menu, measurement, cursors, S-scan, or data. So I'll move my data cursor now back to the middle of the flaw, and I can just scroll it using my mouse. Now we'll do height sizing, menu, S-scan, and we're interested in the ultrasound cursors, and we have 2 of them. So I will place a reference cursor at about the 2 or 3 dB drop from one of the pores of the porosity, and I'll do the same on the bottom side. And I'll take my data cursor and move through the weld, making sure there's not a significant porosity pore. It's easily identifiable with enough amplitude or below the zone that I've identified. And there's not. So we look okay. So what this gives us is a length of 26 millimeters and a through-wall height dimension of 3.3 millimeters with a maximum depth of 4.6. And again, a VIA near the center line embedded in the weld, indicative of slag or porosity based on A-scan, S-scan characterization and position. Another example. Okay, In this example, we have a 16 millimeter weld, V-weld, with one indication, and as I roll through the data, I can see multiple facets, jagged A-scan, lots of peaks, very typical of a crack. It should be immediately identified by the trained phased array operator, distinguishable from root fusion, inadequate penetration, or other types of defects, including geometric indications as well. So it's clearly connected to the ID. So I can perform my length sizing quickly. If I put the display in cursor mode, and I'll just drag and drop the cursor to about the 6 dB drop position. I'll move my index cursors out of the way and zoom in on my flaw. Every one of these distinguishable different signals is a different crack or branch or facet of the flaw. When we're doing shear wave tip diffraction, even the smallest little indication can be an indication of the crack. So we have a clearly distinguishable one here. This is the main signal we see from the corner trap, and this is the next branch of the signal we see here. And there's even a smaller one at the very top that we see here. And as I move the probe back and forth, I can see that little tip. And as long as it's clearly distinguishable from the baseline noise, I can call that the branch of a crack. Another good technique we would use is the B-scan. Changing the layout to the A-B-C scan, I get the same A scan and B and C scan, but now I can look at the projection of one single focal law over the whole UT range. So I can see my length sizing and individual different tip facets of the crack from a side view. So menu, measurement, cursors, data, and as I change my angle and roll through the flaw, at this position, we can clearly see, the geometry at B0. And we can see the different branches and facets of the crack. And I hope this is coming through for the webinar video presentation, but there's a tiny little tip right up here. Here is another very clear branch of the crack, and as if I were to roll through all of it, I will see that indication come right out of B0 where the back wall is, and look at the various branches and tips of the crack, clearly indicating it's a crack with multiple peaks and edges. And the idea is to find the deepest one you can and identify it. Moving on to our last example. This is a clock scan of a technique similar to the WSY ID creeping wave probe. I'm going to turn my scan axis to this direction, and I'm going to walk the probe on the clock inspection using the ID creeping wave. What this does, this is an L-wave wedge with a 55 to 70 degree sector scan. For those of you familiar with the technique, this is the high angle L wave. This is the mode converted shear wave at 30 degrees approximately. And this signal is the ID creeper. So that technique is very common in conventional UT, and we do the same thing with the phased array. And this is an example of where the S-scan is going to use a sound path display, meaning the range is exactly the same on all focal laws. This represents me walking the probe slowly towards the weld. As I move towards the weld, the base of the crack or the corner trap starts to appear here, and the tip of the crack appears here. As I continue walking that into the weld, this big signal is the mode-converted shear wave skipping into the crack here. It's traveling at a velocity of half the speed, so it appears farther in time of flight. This indication is the ID creeper. When this signal is present, it indicates that the crack is connected to the ID. When it's absent, it means the crack is embedded. So if we take a look at our deepest tip, like we see right here, and peek him up, we'll change the angle to the tip, and I'll move the data cursor back and forth representing the probe. The envelope feature on this A scan helps me identify the very peak. And if I move my green gate directly over that, we'll have a depth of 12.07. If I move the probe a little bit to another position, move the cursor to the center of the energy, walk the probe back and forth so that I can peak the amplitude, and again, move my gate directly over the tip, I'm seeing the same depth across multiple angles. A very typical high-angle L-wave ID creeping crack detection technique, often used in the power generation in-service detection, and we can see the benefit of the 70 to 55 degree sector scan using the same technique gives us very, very accurate sizing techniques. So we're going to wrap the webinar at this point. I noticed we had a few questions that we're not going to have time to get to. I'm going to answer those via email. I want to thank everybody for attending the session. This is one of many we hope to have in the near future.